Section 4.5 is talking about rational functions and their graphs. And remember, rational functions are going to look like fractions. They're really quotients, which are division problems, right? But they're going to look like fractions to us. And that means we'll have a polynomial in the numerator, or a polynomial in the denominator, and that denominator, the polynomial here, cannot be equal to 0. Change this in your note page. If it has that little 1 in between, it should say not equal to 0. Q of x cannot equal to 0. So we're asked to find the domain of these rational functions and put it in set builder. We'll put it in set builder notation, and then we'll write it in interval notation also. But the domain is basically going to say we have to exclude any x values that would make this denominator 0. So the first thing we have to do with this one is factor it. We need to know what two factors are in that quadratic equation that we've got down here. So I'm going to set it, and I'm going to say both of them have a minus sign. I would say factor the x squared. And then I'm looking for factors of 18 that add together to give me 9. And that's going to be 6 and 3. Both of them are negative. I already set the signs, and then you can FOIL it to check it. So what can x not be equal to? Well, if I set this to 0 is equal to x minus 6, then I would say x is equal to a 6 would make it 0. Same thing for the other one. If I say 0 is equal to x minus 3, then x is not going to be, or it would equal a 3, and either x of 6 or x of 3 has to be excluded. In other words, those would be where my zeros are. That would cause the denominator to be 0. So I'm going to write it like this. I'm going to say x cannot equal 3, and it cannot equal 6. In set builder notation, all I really have to do is add a bar here, an x in front, and put it in these curvy brackets. It says the set of x such that x is not equal to 3, 6. That's set builder notation. And you might want to just make a note because you need to know the notations, right? This is set builder. And then they wanted us to also write it in interval notation. Now we should think about that as a number line. And so it would start at negative infinity, would go all the way up to 3, does not include the 3, it starts right on the other side of that 3, and goes all the way to 6, but doesn't include the 6. And then it goes all the way on the other side of that 6, and goes all the way, sorry, that's a comma, to positive infinity. And there's my interval notation. So those are the two notations that you need to be aware of. Now let's take the next one and see how we can find the domain of this one. Once again, we have to factor that denominator. Well, this is a difference of two squares, so it's easy to factor. I say x plus 3, x minus 3. I know that if I set these equal to 0, I'll find that x cannot equal negative 3, and it cannot equal 3. In set builder notation, all I have to do is add the bar and the brackets, bar, x, bracket. So the set of x such that x cannot equal 3, does not equal 3, or negative 3. Interval notation, I have to say, well, I start at negative infinity, go all the way to negative 3, but I don't include negative 3. And then I join that with the other side of negative 3 all the way to a positive 3, don't include that positive 3, and I join it again on the other side of 3 and go all the way to positive infinity. So there's my two notations that I need to know. Now for the next thing we have to talk about is something called asymptotes. And these are lines, usually we consider them invisible lines, that as a graph it gets closer and closer to it, but it never really touches it. So we have a couple of types of asymptotes that we want to consider. We were going to talk about vertical asymptotes, which would be x is equal to a certain number, or horizontal asymptotes, where y would equal a certain number. The first one we're going to consider here is going to be the vertical asymptote. We're going to figure out how to find the vertical asymptotes of a graph, of a function. So to find these, what we do is we find out the values of x, where, you know, the numerator and denominator of this thing would, sorry, where the numerator and denominator would be factored. And then we're going to set that denominator equal to 0 and find out where, you know, that would cause us, really what we're finding is the domain, the restrictions on the domain again. But this time, we're going to recognize those as vertical asymptotes, okay? So for this one, I'll give you this as an example. We have 3x over 2x plus 8. And first, I'm going to set this denominator equal to 0. I'm going to say 2x plus 8 equals 0 to find out what the restrictions are here. And I would factor out the 2. Or, well, let's just do it this way. Let's just subtract 8 from both sides and divide by 2. And we find that x is equal to a negative 4. Now, that's going to cause a 0 in the denominator. That would be either a vertical asymptote or it would be a hole in the graph. And you have to know which it is, whether it's a vertical asymptote or a hole in the graph. Now, the way we figure that out is we know this is an x of negative 4 is going to cause that denominator to be 0. But would it also cause the numerator to be 0? Well, that would be 3 times negative 4, which would be negative 12, so it's not 0. Therefore, it is not a hole. A hole in the graph causes both numerator and denominator to be 0. So I'm going to say this is a vertical asymptote, and it is x is equal to negative 4. If it had caused both numerator and denominator to be 0, it would be considered a hole in the graph. And I'm going to show you an example real quick. I'm going to use another piece of paper to show you an example of an equation or a function that does have a hole in the graph. For example, let's look at this one. What if we had f of x is equal to x over x squared minus 4x? Now, I'm going to factor that. I'm going to say this is the same as x over, I'd factor out my x, and I'd have x minus 4, x times x minus 4. So I can easily see the restrictions on the domain, which would be the vertical asymptotes. This is going to be 0 if x is equal to 0. It's also going to be 0 if x is equal to a positive 4. How did I find out? Well, I set each of the factors equal to 0. X is equal to 0, and then I said x minus 4 is equal to 0. Well, that would mean x was equal to a positive 4. You might have to write it down, but if you don't, this is okay. So I have 2 vertical asymptotes, possibly. One of them might be a hole. Let's check it out. If I substitute back into the equation 0 for x, I have 0 divided by 0 squared minus 4 times 0. And of course, this is 0 divided by 0. So this one is a hole in the graph. In other words, it's a point right there at x equals 0 where the graph doesn't cover it. We would just draw a little open circle in our graph like this, and the graph would continue on both sides. What about 4? Well, if I substitute 4 in, the numerator does not go to 0. The denominator does go to 0. I know that because I already solved this. 4 minus 4 is 0. 0 times 4 would be 0, right? But I would still have a 4 in the numerator. So I would have 4 divided by 0. So this one is a vertical asymptote. But this one is a hole in the graph. Okay, and that's how you determine the difference in vertical asymptotes and holes. You're really not going to see in your examples many that this condition covers, but you do need to know and be aware of them. Okay, let's check out and find vertical asymptotes for the second example that I've got here for you. X minus 3 over x squared minus 9. And for this one, what I would say is, let's factor it. I've got x minus 3 in the numerator, and I would factor this into x plus 3 times x minus 3, right? Now, I can tell where I'm going to have a vertical asymptote now. I would say my vertical asymptote or hole would be wherever x was equal to a 3 or negative 3, right? So where I'm going to have possible vertical asymptotes would be, setting this denominator to 0, I would have x is equal to a negative 3 or x was equal to a 3. Now I have to check and see, are either of these holes in the graph? Well, if x is equal to a negative 3, this numerator would be negative 3 minus 3, which is a negative 6. It did not turn into 0 itself. The denominator did. So x equals negative 3 is a vertical asymptote. Try 3. If I plug in 3, I'm going to have 3 minus 3 is going to be 0 for my numerator. I already know that this will cause 0 in the denominator. So 3, x equals 3, is going to be a hole in the graph. For page 26, we're going to switch now and talk about horizontal asymptotes. Now, this would be a line y is equal to the value of this line because it's going to go straight across. And it's what the function will approach but doesn't actually reach this horizontal asymptote. And we want to look and see if sometimes there might not be one in the graph, but we'll look for them. I've given some these are the typical directions to locating horizontal asymptotes, and you have to memorize these 3 rules, or you can follow an optional method that I think might be a little easier. And in my optional method, which you might want to copy down, you have 2 steps. First, you set the numerator and the denominator of your function to the same degree. This sometimes means that you have to add an extra term with 0x squared or something like that, just like we've done before when we're doing synthetic division. But we have to have the same degree in both the numerator and the denominator of the function. Once that happens, the leading coefficient of this particular rational expression becomes the horizontal asymptote. We say y is equal to whatever that leading coefficient is. Now, for example, this one, which is the function of 12x minus 1 over 3x plus 2, I would look and say, well, they're both to the same degree. Both the numerator and the denominator are to degree equals 1. So that step 1 is already done. I don't have to do anything to this one. So now if I want to find the leading coefficient, well, here it is. The leading coefficient is 12 divided by 3. And I would say, well, that's actually 4. So y is equal to 4 is my horizontal asymptote. And this always works for us. And it's sometimes easier than memorizing these 3 rules. Next, let's look at this one. This time when I look at it, I see that this is degree 2, but this is just degree 1. So I'm going to have to insert something here. So as step 1 says, I'm going to set both of these to the same degree. I'm going to say h of x is equal to 2x squared plus 5x plus 1. And I would call this one, I need an x squared term, so I'll add it. 0x squared plus 2x minus 8. Now I can take my leading coefficients and I can say that is going to be my horizontal asymptote. Leading coefficient here is 2 divided by 0. Well, 2 can't be divided by 0. This is undefined. Now, if that happens to you, you have no horizontal asymptote. If it was the other way around and it was 0 divided by 2, our horizontal asymptote would be y is equal to 0. Now let's take a look at these just real quick on the TI-84 calculator to see if it agrees with what we've got. Now to enter these, I'm going to go to y equals, and I'm going to put parentheses around both my numerator and my denominator. I'm going to say 12x minus 1, and well, I've got to be over here, sorry. I'm going to say 12x minus 1 and close it, and then I'll say divided by the denominator, which is in parentheses also 3x plus 2. And then I'm going to graph it. Now when I graph it, it looks like that y is equal to 4 being my horizontal asymptote is probably about right. Y would equal 1, 2, 3, 4, right about here, and go all the way across. It looks kind of good for my horizontal asymptote, so that agrees with it. Let's look at this one and see if we can tell that it really doesn't seem to have a horizontal asymptote. And I'm just going to come over here and clear this, and then type in 2x squared plus 5x plus 1. And put that in parentheses and say divided by, in parentheses, 2x minus 8, and close up the parentheses. And that looks right. And let's graph this one. It really doesn't look like there's a horizontal line that it gets close to but never crosses and sort of goes close to. This doesn't look like it has a horizontal asymptote, does it? And that's what we found when we did this leading coefficient. Now on page 27, we're going to look at what we can do with transformations. We can sort of look at these functions, these rational functions, and if we understand what the parent graph looks like, we can still apply our transformation techniques to see what the transformed graph would look like. Let's take a look at this particular parent graph, which is y is equal to 1 over x, and you may remember this one. It uses the horizontal and the vertical asymptotes here are going to be the y and the x-axis, and it comes through 1, 1, negative 1, 1, and then it comes very close to the both axes here, and it really has origin symmetry, doesn't it? Because both of these quadrants, these match the first and the third quadrant. If you flipped them, they would be the same. So that's a perfect y is equal to 1 over x parent graph, and if you know that one, you can kind of see what would happen if we changed it just by adding 2. Now remember, when we add something, it's really it's a vertical translation, and it's basically going to tell us that it wants us to take this graph and go up 2, right? So we're going to really move it up by 2. I'm going to just kind of make a note there. This really just says go up 2. So what I would do is first I would move my asymptotes. I went from these two, and I'll just come down here. I went from the x and y axis. I just kind of went up 2 with it, didn't I? And I've grabbed a different color pen so I can show you what I've done, because the x-axis goes up 2 and it becomes this line right here. But the y-axis, by moving it up 2, it's still the same line, isn't it? I'm just going to see if I can put my orange pen across it so you can see that I didn't really move it. Just by moving it up 2, it didn't change it much, did it? So when that happens, I can pretty easily now just say, what happens to my graph? Well, this graph was at 1, 1. It's still going to be 1 point across from here, and this one's going to be 1 point across here. It got very close to this axis, didn't it? And it would just do the exact same thing, just shifted up by 2. Now I would plot a few more points than just the 2 points that I plotted. You can use your TI-84 to do that, or you can plug in some values for x and solve for y, and that makes it, and it's a pretty easy graph for you to do this. Let's look at another one that's a little more complicated maybe. In this one, we've got to say what happens with a negative out front. Well, this is a reflection. It reflects around the x-axis, doesn't it? It's an x-axis reflection. And then I say inside parentheses here, it says -2. That one is the one that seems backwards to us. That one tells me I have to go right 2. And then my +6 over here says go up 6. Now all I'm going to do is move my axes. I'm going to move my x and y axis, because that's where this thing actually centers around. It's using those as asymptotes. I'm going to move them up 6 and to the right 2. So let's see if I can do that. I'm going to go up 6 with the x-axis, and that will be right here, won't it? I don't have to go right with it, but for the y-axis, I'm going to go to the right 2. So I've got new asymptotes. Now, what else did it do? Well, it reflected, didn't it, around the x-axis. Now, this particular graph, I have to remember what it looks like. Now, in probably thinking about your parent graph first before you do a translation is the best thing to do, but let's look at this one. What the parent graph is for this one is not 1 over x, but it's y is equal to 1 over, and this would be x squared, right? So if I don't remember what that looks like, I go to my calculator, mine's a TI-84, and I just go ahead and type it in, y is equal to, and here's what my parent graph is. I know it's 1 over x squared, and I just want to see it. I'm going to graph it, and this is the 1 over x squared graph. Now, if I do a negative reflection across the x-axis, it's not going to go pointing up anymore. It's going to go down, isn't it? So I've now moved up 6 and to the right 2. I have moved my x and y axis. I've moved my asymptotes. And now all I have to do is turn the graph upside down. So instead of going up like it used to, in the new graph, it will come here and go down. Now I'm just going to draw in a real quick point here because I know that one. That 1, 1, and -1, -1. You could also, if you want more points, and it's a good idea to look for more points, you could also plug more x values in, solve for y, or look what happens when we go to our table. It gives us a lot of different points that we can find. It's pretty difficult to find whole numbers for this one. That's why I let x equal 0.5 instead of just whole numbers, x of 1's, increments of 1, it's increments of 0.5. So that does sort of help me, but still, look, I'm not finding whole numbers. But you can do some math and you can find fractions and you can still graph them. It's basically the same graph, not turned like this, sorry. It's like this. Nope, I'm going to get it right now. Okay, upside down, right? Scratch that out. Now, hopefully that makes sense to you. All it did was reflect around the x-axis. I had the points identified. Everything now should be going down. Now, on page 28, we're going to start doing some more detailed analysis, really about, and this is more like the problems you're going to be solving in My Open Math and the problems you're going to have on your test. But let's take a look at finding first the domain of our function, locating vertical asymptotes or holes if there are holes, finding horizontal asymptotes, and there's going to be at most one horizontal asymptote, and determining the x-intercepts, y-intercepts, and with them we're going to find additional points as necessary to graph these functions. So those are our steps that we're going to go through. The first 5 steps, I'm going to come over here and label. First, I want to find the domain. That means I need to know what the restrictions are. In other words, what would make this denominator equal to 0? Now, if I said 2x minus 4 equals 0, then I would solve it. I would say 2x is equal to 4, and x is equal to 4 divided by 2, which is 2. I know x cannot equal to 2. The domain is going to be the set of x, I'll write it in set notation, the set of x such that set x is not equal to a positive 2. And that is my domain. All right. Question number 2 says locate vertical asymptotes or holes. Now my vertical asymptote is going to be right here. It's going to be where x is equal to 2. Now, is it a vertical asymptote or is it a hole? And I have to look at my numerator up here. I know it would make 2 is going to make the denominator be 0, but would it make the numerator 0? Well, that would be 6 times 2 or 12. 12 plus 12 is definitely not 0. So this is a vertical asymptote, not a hole. Next question. Let's find any horizontal asymptotes. So what do we do this time? Well, this time we want to look at that leading coefficient. Because these are both degree 1, I don't have to add any terms, so I can say the leading coefficient here is 6 divided by 2, or 3, and my horizontal asymptote would be y is equal to 3. Number 4, find x-intercepts if there are any. Well, for x-intercepts, we set y is equal to 0, don't we? So I'm going to say 0, which I know this is really y. 0 is equal to 6x plus 12 over 2x minus 4. Now, what has to happen for this to be 0 is I have to have a 0 in the numerator. So you really, when you're trying to find these x-intercepts, all you have to do, where y is equal to 0, all you have to do is set this numerator equal to 0. You don't really have to worry too much about the denominator. And I would say, because if it's 0, then this entire thing would be 0. So I'm going to say 6x plus 12 equals 0. 6x is equal to a negative 12, and x is equal to a negative 2. And that is going to be my x-intercept. I have 1. It's where x is equal to a -2. Now let's see if we can find y-intercepts, if there are any. Now y-intercepts are going to be where x is equal to 0. So what would y be? I'll say 6 times 0 plus 12, divided by 2 times 0 minus 4. Well, this is going to give me 0 plus 12 and 0 minus 4. And that's going to be 12 divided by -4, which is a -3. So I have y is equal to a -3, and that is my y-intercept. Now, so I know a lot about my graph. I'm ready to start graphing it. The first thing I'm going to do is put in vertical and horizontal asymptotes. Where is x equal to 2? And I'll put a dotted line there, a dashed line right here. And this is x is equal to 2. And then where is y is equal to 3 is my horizontal asymptote. So I go to y is equal to 3, and I draw this one in. Now the rest of the graph, I have to sort of figure it out, don't I? The intercepts will help me. My x-intercept, it's going to intercept the x-axis at x is equal to -2. So I know it's going to cross right here. It's also going to cross the y-axis at y is equal to a -3. So this is sort of telling me a little bit about the graph. I mean, it's getting close to these asymptotes somewhere, but it's not getting close to this center, is it? And I don't really know what it's going to look like on this other side. I don't have any points plotted. I have to plot points to be able to finish graphing it. So you can do it either. You can go and put values in for x and solve for y and plot points on both sides of this x is equal to 2. You want points in where it's less than x, x is less than 2. You want points where x is greater than 2, and you'll be able to find these points. Or you can look at this graph with your graphing calculator. So I'm going to plug in 6x plus 12 as my numerator, divided by 2x minus 4 as my denominator. And then I'm going to say graph. And yes, that does look like what I expect it to look like. I'm looking at the asymptotes and thinking, that's really looking close to what I've got here. But we can't see points until we go to table. And for table, I've got it set to 0.5, don't I? So I'm going to go in and do table set. I'm going to go second window and change my table set to increments of 1. Then I'll go back to table. And now x's are whole numbers. So I can sort of find some points that help me out. I want to go as far over here as I can. If x is a -10, which is the end of my graph, then I see y is a +2. So -10 is going to give me this +2. That's one point I can graph. And then I'm really looking for whole numbers. I see -4, 1 is right here, isn't it? I know the x-intercept. Let's see what I can find that's closer to the asymptote. So I'm going to look for x of, maybe I got -4. I got an x of -2, didn't I? I know that's 0. And then I got an x of -1. I ended up with -1, -1. That's that one. And then I ended up with 0, -3. Well, that's true because that's the y-intercept. What happens after that? I ended up with 1, -9. And then I got an error. Why? Because that's the asymptote, isn't it? And it's never going to touch that. So I've got this part of my graph that I can do a really accurate depiction with. And that looks like this portion. Now let's go over to x greater than 2. I need to get my x values bigger than 2. And the first one I see is 315. So when it's 3, it's all the way up at 15. I can try and figure out where that is. It's going to be up here somewhere. Let's get closer to home. 4, 9. 4 is going to be right there. And 5, 7. And if you did the calculations with these, if you plugged in 5, you would get 7 for y. You could do all this math with your calculator or by hand. 6, 6 is 1. or you can use your graphing calculator. And then I've got 8, 5, and that's probably enough. 9 is not a whole number, 10 is not a whole number. I'm going to just use those. I'm going to kind of go right here, and I've got a really good idea of where this goes. So there's my pretty accurate depiction of my graph. So let's take these principles and these procedures that we've learned, and let's apply them to some more complicated graphs. This one is 3x plus 6. This function is 3x plus 6 over x squared minus 9. Now I'm going to take it and go ahead and factor it. And normally I would factor out the 3. And I would factor the denominator, although factoring that numerator is not really necessary for what we're doing. So I factored the denominator as a difference of 2 squares. And then the first step, of course, if you remember, is finding the domain. Well, I find that the domain says that x cannot be a negative 3 and it cannot be a positive 3. So I'm going to say it's the set of x such that x is not equal to negative 3 or positive 3. And that's, of course, set builder notation. And I'm going to write out here that what this is, we found the domain of this. Now, once we've found the domain, we've really found the vertical asymptotes, haven't we? Or we've found holes. Let's look at that and see. If x is equal to a positive 3, it still wouldn't cause 0 in the numerator, would it? Because this would be 3 times 5, and that's 15. So what if x is equal to a negative 3? It would be 3 times negative 1, which is not 0. So both of these, 3 and negative 3, are going to be vertical asymptotes. Now, number 3. I've got to see what the horizontal asymptote is, if there is one. And the way I'm going to do it is see if I can get these leading coefficients, but this is not the same degree. This degree is to the first degree, and the denominator is to the second degree. So I would actually change this. I would say add the function, I'll say this is f of x, would also equal 0x squared, right? Plus 3x. Plus 6. Now, really the only term that you need is the first term, but I'm going to fill it all in for us. This is still x squared minus 9, and now I can say, well, that's a 1. What's the leading coefficient here? It's going to be 0 divided by 1, which is 0. So there's my horizontal asymptote. Horizontal asymptote, y is equal to 0. And technically, that's always going to happen when you have a smaller degree in the numerator than you do in the denominator, isn't it? All right, so let's look at this one. Next one is step number 4. What we're supposed to find is x-intercepts. So we set y is equal to 0, and we're going to solve these. Well, y is equal to 0. That's going to happen if the numerator of this problem is 0. So all I have to really do is set the numerator to 0. And solve. And so that would be 3x is equal to a negative 6. And that's going to be x is equal to a negative 2. And that's going to be my x-intercept. Y-intercept, of course, is where x is equal to 0, isn't it? So for y-intercept, I'm going to put x for 0x into my function. I'm going to say 3 times 0 plus 6 over 0 squared minus 9. Well, these are both going to be 0. So what I've really got is 6 over a negative 9, which I can reduce that. It's going to be a negative fraction. Divide both of them by 3. 6 divided by 3, 9 divided by 3, and I end up with a y is equal to negative 2/3, and that is my y-intercept. Okay, so I've got a lot that I need to graph this one. It's an unusual one because it does have 2 vertical asymptotes. So let's put those in first. X is equal to 3 and x is equal to a negative 3. And that would, of course, be x is equal to a negative 3. And here's x equals 3. So I've got my 2 vertical asymptotes down. And now I'm going to say, where's my horizontal? Well, it's here. Basically, I'll just see if I can make my dashes look bigger on the x-axis, right? It's going to be y is equal to 0. That's my horizontal asymptote. So I've got this thing, it looks like it's divided into 6 pieces, 1, 2, 3, 4, 5, 6. And my graph will be in here somewhere. And this looks like it's going to be an interesting graph. I'm probably going to need my graphing calculator to show me what this thing looks like, because I'd be plotting an awful lot of points to see if I could find it. And that's entirely possible, but let's use the graphing calculator to look at this one. First, let's see, do we have an x-intercept? Well, it says x is equal to -2 is where it's actually going to cross. So I'll fill that one in. Y-intercept is y is equal to a -2/3, right in here somewhere. So this looks like it's going to cross and maybe do this S shape in the center. I don't know what it's going to do on the ends. I'm kind of going to depend on my calculator to help me with this. I'll go y equals and clear that out. And then I'm going to type in the numerator, which is 3x plus 6 divided by the denominator. And remember to put both of them in parentheses. This is going to be x squared minus 9. Close them off, and let's graph this. And if you can imagine the asymptotes drawn in here, the 2 horizontal ones, the 2 vertical ones, the horizontal one is, of course, the x-axis. And then you can sort of see that it did have my S shape here, and it does mirror images of this other curve on the sides. And I'm going to go to my table to get some values. Now this one, I'm going to just go ahead and use these values, even though they're all fractions and decimals. I can try to go to table set and set increments of table to 0.5 instead of 1, and then let's see what the table values look like now. They're still not whole numbers, are they? But if I want to come over here to where x is less than a -3. So I'm going to say if x is a negative, what, -4, -3.6, something like that, or -4, I've got a y value of -8.6, okay? So when x is a -4, my y value is going to be right around here, close to 1. I can put a point there. And then I've got where x is a negative, it's not going to cross this asymptote, but where x is a -3.5, I've got y of -1.38, so it's a little over that. 3.5 is going to be right below here, somewhere in here. It's starting to turn. You can tell it's starting to turn. It's going to get close. I know it's going to get close to both asymptotes, so I can use that. And then I've got, of course, 2, 0. That's a different part of the graph. I know that's going to be my S-shaped graph, and I'm going to have to kind of back up here and see what this one does. At x of -5, my y is like 0.5, so I can see it's getting close. Okay, I'm going to say it goes really close to this asymptote, comes up, does a really close turn, and goes very close to that one, sort of like that. That looks like that part of the graph. Now let's see if we can do the center of the graph. We've already got 2 points in the center because we had 2 intercepts, but if we go to a -2.5, we have 0.5. So right up here, it's starting to turn. I know it's not crossing this asymptote, so it's going to go up. And then I'm going to turn it. I know it's got to turn here somewhere. Let's go toward x equals 0, shall we? X equals 0, we know what that is. And then let's go over to x of 1, and we have a y value of -1.12, something right in here. I can sort of guess. And if I have an x of 2, I've got a y value of -2.4 right in here somewhere. And as I get closer to 3, I mean, when I do 2.5, I've got a y value of almost 5, don't I? 2.5, I've got almost 5. I'll come it right in here. So I can sort of say this is kind of the shape it's going to take. And once again, my graphing calculator really helped me determine the shape of this one. Okay, the other section of it is over here, and I know from my graphing calculator it's going to form up in this quadrant. So I'm going to go past an x of 3, and when I get 3.5, right about here, I've got a y value of a little over 5, right about there. And then I'm going to go to 4, and I've got 2.57. 2.5, something in there. And then I've got, let's see, let's go to 5, 1.3, right about here. And then let's see what 6 is. 6 is just under 1, isn't it? And one more. Let's look at 7. It's a little over half, isn't it? Something like here. And I guess I can keep on going. Let's get to 9 and see what it does. Still really close to half, just under half right here. Okay, so I've got these points, and I can pretty accurately draw what my graph looks like. Okay, and it does match what my graphing calculator said, so I'm pretty sure I've got an accurate graph. Now this next one is a bit of a challenge and sort of a conundrum because it's going to have 3 different sections again, and you're not going to actually have to graph too many that are this way. So what I'm going to do is pull this one off of your explanations. I will show you what it does. It forms 2 vertical asymptotes and 1 horizontal, like our graph above it did, but this time it does come down on this side and sort of touch the the horizontal asymptote of 0. And that can happen when you've got sections of your graph. One section follows the asymptote and another section does not. This one I'm taking, like I said, off of your instruction because you're really not going to have to deal with that too much in this course. So continue this one on just if you want to see my explanation for how this works. First, I'm going to look for the domain, and I would factor this denominator. It's a difference of 2 squares. It's going to be x plus 4 and x minus 4. We can do that pretty simply. We'll say this is going to be the set of numbers of x such that x is not equal to -4 or +4. So then we have to look at these and say, are they vertical asymptotes or are they holes, right? Well, if I made -4, I know it'll cause 0 in the denominator, and it does not cause 0 in the numerator. -4 plus 6 is not 0. 4 plus 6 is not 0. So I can say that these two, x is equal to 4 and x is equal to -4, are my vertical asymptotes. And this, of course, was the domain. Now, what was the third question? It was asking us about horizontal asymptotes. For this, I need the leading coefficient, and this term is not x squared. So what I would have to do is set this function, insert the x squared term in the numerator. It would be 0x squared plus x plus 6 over x squared, which is a 1x squared, minus 16. My leading coefficient, therefore, is 0 divided by 1, which is 0. And y is equal to 0 is, once again, my horizontal asymptote. Same as it was in that example above. Okay, so I've got 2 vertical asymptotes. I've got 1 horizontal, very much like I had in the example above. And then for this one, the next thing I'm looking at is what is the x? Is there an x-intercept? So I say y is equal to 0, only if this numerator is equal to 0. And that means that x would equal a -6. And that would be my x-intercept. And the next question is, what are your y-intercepts? Well, that's going to happen where x is equal to 0. So I'm going to say y would equal 0 plus 6 over 0 squared minus 16. Of course, this is 0 and this is 0. This means this is 6 over -16. And that's going to give me -3 over 8. So y is equal to a -3/8 is my y-intercept. Let's start graphing this thing a little bit. I'm going to draw in my asymptotes. I've got x of -4. X is equal to a -4 right here. So that's x equals -4. And I've got x is equal to +4 right here. And my horizontal asymptote was once again y is equal to 0. Now, this graph has some interesting things about it. Like I told you, it's going to, in one of the parts of it, it is actually going to cross one of the asymptotes, which is okay. The asymptote still applies to the other sections of the graph, but that's it's a bit unusual for us. Let's look at the intercepts. One of them is right here, and that's where it actually touches the asymptote, which that's okay, but it doesn't usually happen for your graphs. And the y-intercept is y is -3/8, right in here, about almost half, right? So here's my two intercepts, and the only other thing I have to do is, and I'm going to plug this into my calculator and see what this graph looks like. I almost have it here, but I'll clear this out and say I need the numerator to be x, is it +6, right? Divided by a denominator of x squared minus 16. And now I'm going to graph this. And there it is. And you can see it actually touches this asymptote. So the asymptote applies to these two sections of the graph, but it doesn't really apply to this section. However, the vertical asymptotes do apply to both of them, and this horizontal one applies to this section and these two sections of the graph. You can tell when you look at the table, if you start plotting points, you're going to see that this one is going to come really close. Let's see if I can go back to graph and show you how it's going to do. It's going to come really close to this asymptote. It's going to cross it actually, just barely below it, and then it'll start, if you follow along with your points, it'll go barely below it, and then it'll start inching back up toward the asymptote. Strange graph. And this part of it is going to be totally down. I'm not going to plot all these points because, like I said, this one is not one that you're really going to have to do too much with. It actually comes closer in here than I've graphed it, or shown it to be. But over in this one, and you would need points to show you where it goes, but this is basically the direction it takes. And once again, it does cross this asymptote for this section, so the asymptote just applies for these other two sections of the graph. Okay, a little bit complicated, one you don't need to worry about too much, but you can still do it. Using our principles, you should be able to find the asymptotes, the x and y intercept, and the domain of the graph.